Hello, we are working in chapter 7. We will be looking at shear and moment diagrams. We talked about internal loadings in the last module 7.1, and we looked at shear in a beam. So what exactly the shear is at one point in the beam. Now if you wanted to look at the whole beam, the best way to be able to analyze the shear and the bending moment would be through a diagram. So we could look at this graphically. Now the best way to help understand this is to do a couple of examples. So I'll do this example and then I'll do another example on a separate video. So what we have here is we have a simple beam. We have a distributed load of 10 kip per foot from point A to 5 feet away, and then at 10 feet from point A we have a 10 kip force acting down, and then 15 feet away from point A I have a 2 kip foot couple acting right there, and then I have my pin at point B. So the process of this would be to draw the free body diagram, and if I were you guys, I would actually take the actual roller off and draw your reaction forces. Here you have Bx and you have By and you have Ay. I would also note that you have a equivalent point load of 10 kip feet times 5 feet, which is going to be 50 kips, acting 2.5 feet away from point A. So we need to find the reaction forces, and reaction forces will make or break your shear moment diagrams. In fact, they'll make and break anything they have to do with any problems when you're looking at your reaction forces. So in order to solve for my reaction forces, I'm going to sum my moment about point A here. And please stop the video, work this out, and then come back to see if your answer matches mine. So I have a 50 kip force rotating around point A in a clockwise manner, so it is negative 50 kips, and that is 2.5 feet away. I have negative 10 kips times 10 feet. I have a negative 2 kip foot couple, and then I have plus By times 20 feet. It's all equal to 0. Again, I only have 3 reactions. This is a simple beam with a roller and a pin. So doing the math in my calculator, I came up with By was 11.35 kips. If I sum my forces in the Y, I got that you get 11.35 kips minus 50 kips minus 10 kips plus Ay is all equal to 0. So Ay came out to be 48.65 kips. So here and here. So now let's go to our shear moment diagram. You start on the left side of the beam, so we're starting at our roller. And at our roller, what is happening? Well, I have a reaction force pushing up, and we calculated that to be 48.65. So I'm going to come up here. I'm going to call this point 48.65 kips. Now I have a distributed load. So this distributed load is pushing on this beam the entire time at 10 kip per foot. So knowing that, I'm going to be dropping diagonally, because it's pushing on there, down to here at this point here. And this down here would be 48.65 minus 50, so this is going to leave us at 1.35 kips down below. So it'd be a negative 1.35 kips if you will. Now nothing is happening on the beam between 5 feet and 10 feet of the beam. So this just, our shear stays at 1.35 kips. At this 10 kip force, we drop another 10 kips. So we get now down to 11.35 kips. Nothing happening on the beam as far as shear goes. Now there is a couple, but that has to do with the bending moment, has nothing to do with shear. So this will continue all the way across to 11.35 kips. And this is your check. At BY, we computed that the reaction force was 11.35, so this just kicks straight up, lands at 0, so we should always close at 0. So our shear moment diagram should always close. Now in order to calculate our bending moment, really simple using geometry, we can solve for each shape. Now in this example here, we have this tiny distance, and then we have this distance here that we're going to need to find in order to solve for our areas, because we need base times height. So we need our base here. We have our height here, but we need our base. So I'm going to call this x, and I'm going to call this piece 5 minus x. So I'm going to use simple or similar triangles. This big triangle is similar to this smaller triangle, and I come up with 48.65 kips over, now this goes up 48.65, I'm calling my height, or my base here x, so that's over x, is equal to 1.35, which is my height here, and then my distance here is 5 minus x. So I do my cross multiplication, and I come up with 243.25 minus 48.65x, that's just 5 times 48.65, and then x times 48.65 is equal to x times 1.35. Take this to the other side, and then I will divide that into 243.25 to get x by itself. I come up with x is 4.865 feet. So this was 4.865. And then this piece here came up to be 0.135. It's just 5 minus 4.865. So computing my triangle then, it's 4.865 times 48.65 is 118.3, and that's going to be a kip foot. So this is feet, this is kips. So now you can notice I have a bending moment. I have a moment with my units, which I'm going to be using down here. This little tiny triangle was 0.135 times 1.35 divided by 2. I got 0.091 kip feet. This is 1.35 times 5. So this little area here is 6.75 kip feet. Now I'm going to break this up, this piece here. Now you could do this whole triangle or this whole rectangle if you want, but I'm going to break it up because I have this couple here that I'm going to have to take into account when I'm drawing my moment diagram. So I get 11.35 times 5 feet comes out to be 56.75 kip feet. So I'm going to have the same thing here. Now I'm going to use all of the information that I've come up with and bring it down here. So I have 118.3 kips feet, 0.091 kip feet, 6.75 kip feet, 5.675, 56.75, and 56.75. So something I found on the internet a couple years ago, and I'm going to give him credit here. This is called Kahn's bug. And Kahn's bug helps us draw a shear moment diagram. If this is 0 and our x, I'm not going to call it 0, I'm going to call it my x and my y. So anything below this is negative, anything to the left of this would be negative. So if I'm looking at Kahn's bug and I draw his little arms, this goes like this, and then this goes like this. So I am looking at this, it's a shear, and it's above the x-axis. So I come over here, I'm above the x-axis, and it's coming down. So my line is going to be concave up, as so, to this point right about here. It's not quite at that 5 foot. It's only 4.865 to there. And that's going to be 118.34 kip feet. Now, this is below the x-axis, so I come over here. This is below the x-axis. It's still dropping down, so it's going to come down just a little bit, just like this. That's an arc, just like that. You subtract off the 0.091, you get 118.24 kip feet. Now, we have this rectangular here. This is linear, so now this we're going to have, I'm going to redraw that. We're going down 6.75 feet, kip feet, down to, I'm going to redraw that one more time. It should be about right there. At 111.49 kip feet. Now I'm dropping down 56.75, so I'm going to come about right there. 56.75. I apologize. That's going to be 54.74. 54.74. So 111.49 minus 56.75 gives me 54.74. Now I have this couple. When I have the couple on the diagram, this we always call a negative moment, right? Negative couple because it is going clockwise, and we've called this positive. Well, when you have a negative couple on the actual beam itself, the moment diagram is going to show a positive, and it's going to be vice versa. For a positive moment, it's going to show a dip in your moment diagram. So you notice this is going to be a negative 2 kip feet, so it is actually going to jump up at 56.75 kip feet. And then from here we drop straight down, or 56.74 straight down, because I had 56.75 here, minus 56.75 drops down to 0, and it closes. So that would be my moment diagram, my bending moment diagram. So by looking at this, I don't have to do every single point to analyze shear and moment. I can look at my beam here and say, okay, my shear is this, my moment is this, at any point along the beam. Now, my moment max is 118, so my moment max, bending moment, is 118.34 kip feet. And my shear max is the largest shear, which is going to be up here at 48.65 kips. That's what we'd normally be looking at. That's what you would be designing your beam for, looking at materials, etc., so that it would be able to withstand that shear and that bending moment. So that's a simple beam. The next one is going to be a fixed beam and solving for the shear and moment diagram. I'm probably also going to be uploading another video helping you come up with the equations for each section of the beam in order to plug and chug and solve for a shear moment. Just because I look at this, and if you ask for the moment, we'll say 2 feet away, if that was 2 feet and I wanted the bending moment, we would need to come up with our equation. It's going to be some kind of quadratic equation there in order to solve for that bending moment. We could easily solve for it here using similar triangles again and solving for our shear. Okay, thanks for listening.